Students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as EMI. Let's see what happens if a coil is connected to an AC circuit. Let's see application of AC to a pure inductor. Now, let's connect a coil in an AC circuit. Let's assume EMF source E, current I, and you have coil inductor L. Okay. Let us assume, let I be the instantaneous let I be the instantaneous value of current. Then we have already derived that I is equal to I0 sin omega t. We have derived that the instantaneous current in an AC circuit is equal to I0 sin omega t. Now, due to the alternating current, an EMF is going to be induced in the coil as the current changes. This is an alternating current. This alternating current is going to induce an EMF in the coil. So I can say due to the alternating current, an EMF is induced in the inductance coil. And it is equal and opposite to the applied EMF. The EMF that will be induced in the coil will oppose the very source that produces the EMF. Therefore, I can say EMF is equal to L into di by dt. Same basic Ohm's law. I'm still applying Ohm's law. E is equal to IR. So this is my EMF that is generated. This is the resistance and this is the change in current. Right? Now, therefore I can say that E is equal to L d by dt of I. I we have said is I0 sin omega t. So I can say E is equal to L into I0 d by dt of sin u. Sin u is cos u du by dt. Dt of omega t, which is going to be nothing but omega. So in that case, this is going to be E is equal to omega L I0 cos omega t. Fine, do we get this thing here? Now, let us assume that I0 L omega is say E0. Thus, I can therefore say that E is equal to E0 cos omega t. Fine, do we get this thing here? Now, where I can say E0 is the peak value of EMF, where I can say that E0 is peak value of EMF. Right? Now I can also say from this that E is equal to E0 cos omega t can be written as sin pi by 2 plus omega t. Sin pi by 2 plus theta is nothing but cos theta. So cos theta can be written as sin pi by 2 plus omega t. Right? From this, what we understand is that the EMF is 90 degree. There's a phase difference between EMF and current, and that phase difference is going to be 90 degree. So I can say that if this is how this is going to be my vector representation of the current and EMF. Current and EMF. Right? the EMF leads the current by pi by 2, right? So, and if I were to show it to you in terms of diagram, this is my vector diagram for them. If I were to show it to you in terms of wave, suppose if this is my EMF wave, where I'm assuming EMF and current both on x-axis, on y-axis, and time here, in which case I would have, say, this is, say, pi by 2, pi, 3 pi by 2, and 2 pi. So in which case this would be this is going to be my current wave. If that is my EMF wave, then this is going to be my current wave, right? Now, it can be seen very clearly that there is a 90-degree phase difference between the EMF and the current. The phase difference between EMF and current is 90 degree, right? I can say that the EMF leads the current, EMF leads the current by a phase angle of pi by 2. Or 90 degree. Fine, do we get this thing here? So that's going to be my phase difference. Now we have also said that the peak value of EMS, also the peak value of EMF, the peak value of EMF E0 is going to be nothing but omega L I0. We had assumed this right when we were deriving the equation. Therefore, I can say that omega L is E0 upon I0, right? Now, let's divide numerator and denominator by root 2. If I divide numerator and denominator by root 2, I'll get therefore omega L. Therefore, I can say omega L is E0 by root 2 divided by I0 by root 2. So I can therefore say omega L is E upon I, right? That is E RMS upon I RMS, right? Where E is equal to E0 by root 2 and I is equal to I0 by root 2. Remember, I had explained this to you that to convert from peak value to RMS value, you have to divide by root 2, right? Where I can say that E and I are the RMS values of EMF and current, right? So thus you get omega L is equal to E upon I, right? Now, if omega L is E upon I, let's apply Ohm's law to this, right? If I apply Ohm's law to this, that means omega L is the effective resistance that the coil is going to offer to the current that is going to be flowing through it, right? By applying Ohm's law, if I apply Ohm's law, by applying Ohm's law equation, I can say the quantity omega L represents the effective resistance of the inductor to the flow of alternating current, like how a resistor offers opposition to the flow of current, direct current. Similarly, an inductor offers an opposition to the flow of alternating current, and we will call this as inductive reactance, right? Effective resistance of the inductor to the flow of alternating current, which it is called as inductive reactance. So what is inductive reactance, guys? Inductive reactance is nothing but it is synonymous to the resistance offered in a DC current, DC circuit. How you have resistance offered in a DC circuit, the resistance offered in an AC circuit by a coil is called as inductive reactance, right? Symbolically represented as XL, right? So thus I can say that therefore inductive reactance is going to be omega L, because omega L was the quantity that represented the opposition to the flow of current. But we know that omega is nothing but 2 pi f, but omega is 2 pi f. So therefore I can say that XL is nothing but 2 pi FL. Thus the inductive reactance is given by the formula 2 pi FL, right? So I can therefore say what is inductive reactance. Inductive reactance can therefore be defined as the ratio of the RMS EMF to the RMS current, right? From this equation, as omega L is E upon I, therefore I can say that definition inductive reactance can be defined as the ratio of effective voltage across the inductor, effective voltage across the inductor to the effective current passing through it. Fine, do we get this thing here? Since F is expressed in Hertz and L is in Henries, therefore I can say XL is expressed, since its opposition, it is expressed in ohms. The unit for XL is ohms. Fine, do we get this thing here? So do we understand how an inductor works in an AC circuit? Now let us see how a capacitor works in an AC circuit. Let's see application of AC to capacitance. Let's consider an AC circuit with a capacitor in it. This is current I, this is EMF E, and this is your capacitance C. Right? Now, so let's consider, let us assume, let the instantaneous current in the circuit, the current in the circuit, the instantaneous current in the circuit, the AC current in the circuit we have derived as I0 sin omega t, right? Now let us assume that Q is the value of charge on the capacitor. Let Q be equal to the charge on capacitor, right? And if Q is the charge on the capacitor, then I can say that the voltage drop across the capacitor, the voltage drop across the capacitor will be equal to Q upon C. We know that EMF is charge upon capacitance, right? And it is going to be equal to EMF, and it is equal to the instantaneous EMF applied across it, equal to the instantaneous EMF, right? That means I can say that the EMF is going to be equal to, by the capacitance circuit we know that EMF is equal to Q by C, and because this is an AC circuit, the EMF is going to be equal to E. Therefore I can say E is equal to Q by C. Once you have the value of E, then I can say that the current is the rate of flow of charge, but current is defined as rate of flow of charge. If current is defined as rate of flow of charge, that means I can say I is dq by dt. Therefore I could say that dq is equal to I dt. Right? Now integrate both sides. If I integrate, I'll get integral of dq is integral of I dt. Integral of dq is going to be nothing but q is integral of small I, instantaneous current. We had said is nothing but I0 sine omega t dt. Right? Take I0 out, constants comes out, integral of sine omega t dt, right? Integral of sine theta, right? Integral of sine theta is going to be nothing but minus cos theta. So Q is equal to minus I0 cos omega t upon omega. Whatever is the number with x has to come down in the denominator, basic rule of integration. So thus I now know the value of Q. Once I know the value of Q, I can say but E is equal to Q upon C. So E is equal to Q minus I0 cos omega t upon omega into C. I'm substituting the value of Q. Integral constant? Yes, I will use that. Just give me a second. I'll get the constant. Right? Okay. Now once I have this, I'll get E is equal to minus I0 omega C cos omega t. Right? Now I can therefore say that let us assume I can say that I0 omega C minus cos omega t. I'm taking the minus sign with the cos function. Now sine I want this can be written as I0 upon omega C. This can be written as sine omega t minus pi by 2. If I move clockwise, then in that case I can say that you will get this minus cos omega t as sine omega t minus pi by 2, right? In which case I will also assume, let us assume that I0 upon omega c is E0, where E0 represents the peak EMF. Therefore, I can say E is equal to E0 sine omega t minus pi by 2. Right? Once you have this equation there, right, what we understand from this is that if I compare the EMF and the current equation, what we see is that the EMF lags the current by pi by 2. Right? See here, the also I can say that the current equation was I0 sine omega t. This is sine omega t minus pi by 2. That means I can say that the EMF lags the current by 90 degree. Vectorically, if I want to show you the vector diagram for this would be my current and the EMF would lag this. This is going to be my vector diagram for this. This is E, this is your vector diagram. And if I want to show you in terms of wave, I'm considering EMF and current. I'm considering EMF and current both here. This is 0, pi by 2, pi, 3 pi by 2 and 2 pi. Right? Let's assume that this is my EMF. If this is my EMF, that means the current has to lead by 90 degree. It has to lead by 90 degree. That means it will start this way. It will peak itself here. Right? This is going to be my current wave then. In terms of wave diagram, this is going to be the wave diagram of EMF and current. Fine, do we get this in here? Considering time here. Right? So I can therefore say that the EMF lags behind the current by 90 degrees. Right? Okay. Now also we have said that E0 is nothing but I0 upon omega c. We have assumed this. E0 is I0 upon omega c. Therefore I can say that 1 upon omega c is nothing but E0 upon I0. I'm taking the I0 down here, cross multiplication, right? Divide numerator denominator by root 2. If I divide numerator denominator by root 2, I will get 1 upon omega c is nothing but E0 by root 2 divided by I0 by root 2. So I can say 1 upon omega c is ERMS upon IRMS, right? Now, where I can say that E0 by root 2 is equal to E is the RMS value of EMF and I0 by root 2 is RMS value of current. Right? Now if I apply the Ohm's law equation to this, 1 upon omega c is E upon I, right? By applying Ohm's law equation. If I apply Ohm's law equation, E upon I should be equal to resistance. So I can say that if I apply Ohm's law equation, I can say that the quantity 1 upon omega c represents the effective resistance of the capacitor to the flow of alternating current. DC current. Fine, do we get this thing here? And this effective resistance is called as capacitive reactance. It is called as capacitive reactance and is denoted as XC. That is going to be my capacitive reactance. Thus, I can therefore say that capacitive reactance is 1 upon omega C, but omega we know is 2 pi f, but omega is 2 pi f, therefore capacitive reactance is 1 upon 2 pi fc, right? So that is going to be my capacitive reactance. Fine, do we get this thing here? Now, as 1 upon omega C is E upon I can define capacitive reactance as, I can say that capacitive reactance can be defined as reactance can be defined as the ratio of effective voltage across the capacitance to the effective current passing through it. That's how you define effective capacitance. Fine, do we get this thing here? And I can say that Xc is expressed, since it is opposition to the movement of current, it is also expressed in ohms, right? Next, let us see the difference between resistance and reactance. What's the difference between resistance and reactance, right? Now we have already found out that inductive reactance XL is nothing but 2 pi FL, and capacitive reactance Xc is 1 upon 2 pi Fc, right? Now, where I can say that in case of reactance, reactance is the same as effective resistance. The only thing is that they differ in the respect that I can say that reactance represents effective resistance, right? The difference between them is that first, resistance possesses a constant value throughout the circuit, right? But the value of reactance is not constant, it depends upon the frequency. First, resistance possesses a constant value, right? But reactance, if you can see the equation, it is 2 pi FL. If I change the frequency, automatically my reactance will change. Again here, this is 2 pi FC. If I change the frequency, automatically my reactance will change. I can say, but reactance is not constant and depends upon the frequency of AC. It depends upon the frequency of AC. Hence, I can say that it increases and decreases with the frequency. It increases and decreases with frequency. So, resistance remains constant, whereas reactance increases or decreases with frequency. Right? Next, the second point of difference I can say is that in case of resistance, the voltage across the resistance is always in phase with the current. Right? In case of resistance, the voltage here across the resistance, is always in phase with the current. Right? So the voltage and current are going to be in phase in the case of resistance, whereas in the case of reactance, if it is inductive reactance, it is going to lead by 90 degree, and in the case of capacitive reactance, it is going to lag by 90 degree. Right? In the case, but in case of inductive reactance, E leads I by pi by 2, and in case of capacitive reactance, E lags I by 90 degree. In one case it leads by 90 degree, in the other case it lags by 90 degree. Hence, introduction of reactance in an AC circuit produces a phase difference in the EMF. I can say hence introduction of reactance in an AC circuit produces a phase difference of pi by 2 radians. Right? So resistance does not know this. Now, when electric current passes through a resistance, the electric energy is converted into heat energy, and thus power is dissipated in the circuit. But in the case of AC circuit, with inductance or capacitance, the average power dissipated in pure inductance and capacitance is going to be equal to 0, because the positive half cycle would ideally cancel to negative half cycle. Thus, the loss of power in an inductive or capacitive circuit is 0. So there is more loss of heat in the case of a DC circuit, and there is less loss of heat in an AC circuit. Hence, I can say that an AC circuit is more efficient as compared to a DC circuit, because there is no loss of heat in the case of an AC circuit. Right? Third point, when electric current passes through a resistance, electrical energy is converted into heat energy, and power is dissipated in the circuit. dissipated, right? So that's in the case of resistance. Now, in the case of AC circuit with inductance and capacitance, in the case of AC circuit with inductance and capacitance. In the case of an AC circuit with inductance and capacitance, the average power dissipated is equal to 0. The average power dissipated is equal to 0. Right? Thus, the loss of power in the circuit is 0. Loss of power in the circuit is equal to 0. Fine, do we get this in here? So do we understand the difference between resistance and reactance? Right? We'll stop this here for the day. Thank you very much.